Celsius. This is where the characteristic chocolate aroma begins to develop as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids and are now ready for the next phase, grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel where the caramel layer is firmed to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number. and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients: glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor brix levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc., and it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. The process begins well before any chocolate is poured or any peanut butter is mixed. It starts with sourcing two critical ingredients: high-quality peanuts and specially formulated chocolate. The peanuts arrive at the plant in large, tightly sealed containers, having already undergone preliminary sorting at dedicated processing centers. However, the Reese's factory does not take any chances. Upon arrival, each shipment of peanuts is sampled and tested for aflatoxins, moisture content, and flavor quality. Only the best peanuts pass through to the next stage. The first critical transformation begins in the peanut roasting room, a cavernous area lined with continuous batch roasters. These machines look like giant horizontal drums that rotate slowly, while hot air circulates inside, ensuring each peanut is evenly toasted to bring out its natural oils and enhance flavor. Temperatures inside the roasters are tightly controlled, typically between 300 and 350 degrees Fahrenheit, and the roasting cycle can last anywhere from 10 to 30 minutes, depending on peanut size and desired roast level. Workers monitor color readings using optical sensors, making slight adjustments to the roast if necessary to achieve that signature Reese's flavor. Once roasted, the peanuts are transferred via conveyor belts to powerful cooling tunnels. Giant fans blow chilled, filtered air over the peanuts to halt the roasting process immediately, locking in the flavor profile. After cooling, the peanuts pass through a series of magnetic separators and vibrating screens to remove any foreign materials or remaining shell fragments, ensuring absolute purity. Next comes the grinding phase. The roasted peanuts are funneled into industrial grinders, massive machines equipped with heavy-duty steel plates that spin at high speeds. The first grind reduces the peanuts into a rough paste. Then a secondary, finer grind transforms the mixture into the silky, smooth peanut butter that will fill every cup. During grinding, small amounts of sugar, salt, and a plant-based emulsifier are added to stabilize the peanut butter and give it the slightly sweet, distinctly savory flavor that fans recognize instantly. The temperature is carefully managed during this phase, usually kept between 120 and 140 degrees Fahrenheit to ensure the oils remain stable and the texture remains creamy but not runny. The freshly made peanut butter is then pumped into enormous stainless steel holding tanks, where it is kept warm and agitated gently to maintain a consistent texture. These tanks are connected by sanitary piping to the production lines, allowing for seamless and hygienic movement of the peanut butter when it's time to fill the cups. Meanwhile, the chocolate preparation is already underway in a different section of the factory. Reese's uses a specially formulated milk chocolate blend that balances sweetness, cocoa flavor, and a creamy melt-in-the-mouth texture. Bulk chocolate arrives in the form of large solid blocks or liquid tanker shipments, depending on the factory's setup. If solid, the chocolate is first broken down in massive pre-melters, slowly heating it to around 110 degrees Fahrenheit to achieve a uniform, molten state. Once liquefied, the chocolate is pumped into tempering machines, sophisticated systems that cool and reheat the chocolate in a precise curve to stabilize the cocoa butter crystals. This tempering process is critical. It gives the finished cups their glossy appearance, firm snap, and excellent shelf stability. Now, with both chocolate and peanut butter ready, the cup assembly line begins. First, paper cup molds are automatically dispensed onto a continuously moving conveyor belt. High-speed chocolate depositor machines then squirt a carefully measured amount of molten chocolate into each paper cup, forming the base layer. The conveyor belt vibrates gently to help the chocolate settle evenly across the bottom and slightly up the sides of each mold. Immediately after this, the conveyor moves the cups through a cooling tunnel, where chilled air at around 50 degrees Fahrenheit partially solidifies the base chocolate layer. This quick cooling ensures that when the peanut butter is deposited, it won't sink all the way to the bottom of the cup, maintaining the ideal layered structure. Next, the creamy peanut butter is deposited into the center of each chocolate base using precision nozzles. The amount of peanut butter is meticulously controlled by programmable pumps, ensuring every Reese's cup has the same perfect peanut to chocolate ratio. Interestingly, the peanut butter filling itself is slightly cooler than the chocolate, typically around 80 to 90 degrees Fahrenheit, which helps it stay firm during the next stages of production. After the peanut butter is deposited, a second layer of molten chocolate is dispensed over the top, sealing in the peanut butter and forming the upper shell of the candy. Again, careful vibration of the conveyor ensures a smooth, even surface. At this point, visual inspection systems using high-speed cameras and AI algorithms scan the cups for consistency, checking fill levels, alignment, and any surface imperfections. Defective cups are automatically rejected from the line. The filled cups then pass through an extended cooling tunnel where they spend several minutes gradually chilling back down to around 45 degrees Fahrenheit. This staged cooling prevents the chocolate from blooming, a condition where cocoa butter rises to the surface and creates an unsightly white film. Instead, the cooling process locks in that deep, shiny chocolate sheen. Once fully cooled, the cups are ready for packaging. Automated robotic arms gently lift rows of finished Reese's cups and place them into pre-formed trays or directly onto flow wrapping machines. Each candy is enveloped in a thin, protective layer of branded orange packaging film. Heat sealers quickly fuse the edges of the wrapper shut, trapping a pocket of nitrogen gas inside. This inert atmosphere helps prevent oxidation, preserving freshness and flavor for extended shelf life. The wrapped candies are then grouped into multi-packs by high-speed cartoning machines, which fold and seal cardboard boxes around designated numbers of cups, whether it's a standard 2-pack, a king-size 4-pack, or a family-size bag of miniatures. These boxes are coded with manufacturing dates, lot numbers, and other traceability data before being stacked neatly onto pallets. Before the pallets leave the factory, a final quality control check is performed. Random packages are pulled from the line and subjected to a battery of tests, including weight checks, taste tests, visual inspections, and even X-ray analysis to ensure there are no contaminants or structural flaws inside the candies. Only when these samples pass inspection are the pallets shrink-wrapped and labeled for distribution. From there, the Reese's Cups embark on their journey through a highly coordinated supply chain. Pallets are loaded onto refrigerated trucks, kept at cool but not freezing temperatures to prevent the chocolate from melting or degrading. Distribution centers across the country receive the shipments, from which they are sent to grocery stores, convenience shops, vending machine suppliers, and even directly to online retailers. What's fascinating about the Reese's production process is how every detail, temperature, timing, movement, is optimized for both speed and quality. The factories are largely automated, with programmable logic controllers and centralized computer systems coordinating every phase, minimizing human error and maximizing consistency. Maintenance crews monitor the machinery continuously, ready to intervene if even the slightest deviation occurs. Yet, despite the heavy automation, a skilled team of chocolatiers, food scientists, and process engineers oversee operations daily, ensuring that the soul of the Reese's Cup, the perfect balance of creamy peanut butter and silky milk chocolate, is never compromised. In recent years, new technologies have further enhanced production. Advanced predictive maintenance uses AI algorithms to detect early signs of equipment wear, preventing costly downtime. Robotic packaging systems have become faster and more flexible, adapting to different product formats with minimal reprogramming. Even energy efficiency has improved dramatically, with modern factories recapturing waste heat from the roasting and tempering processes to reduce overall power consumption. The result of all this effort is what you hold in your hand, a Reese's peanut butter cup with the same incredible taste that has delighted generations. From careful peanut selection to intricate chocolate tempering, from the first squirt of chocolate to the final seal of the wrapper, every step is a marvel of precision, engineering, and culinary artistry, ensuring that each bite delivers the unmistakable Reese's experience, time after time. The making of Hershey's milk chocolate begins long before any bars are molded or wrapped. It starts with sourcing one of the world's most essential commodities, cacao beans. Hershey's purchases massive quantities of cacao from regions like West Africa, Central and South America, and parts of Southeast Asia. Upon arrival at Hershey's specialized facilities, the cacao beans undergo strict quality control protocols. Sampling machines pull randomized beans from each shipment, checking for mold, contamination, fermentation quality, and flavor profiles. Only beans that meet Hershey's high standards proceed to production. The first major operation is cleaning. Beans travel through a series of shaking screens, magnetic separators, and powerful air jets that remove debris like sticks, stones, and dust. Once cleaned, the beans are routed to the roasting department. Here, colossal stainless steel drum roasters, each capable of handling thousands of pounds per batch, bring the beans up to roasting temperatures of around 250 to 300 degrees Fahrenheit. This roasting phase is crucial. It not only develops the rich cocoa flavors, but also loosens the shell from the nib, the part of the bean that will become chocolate. After roasting, the beans pass through cracking and winnowing machines. Heavy rollers crack the beans open, and powerful airflows then separate the lighter, papery shells from the heavier cocoa nibs. The nibs are collected and sent immediately into the refining phase. The shells, interestingly, don't go to waste. Many are repurposed as agricultural mulch or used in animal feed. The next transformation happens in the grinding rooms. Industrial grinders crush the nibs into a thick, gritty paste known as chocolate liquor. Despite its name, it contains no alcohol. Giant stone mills or modern ball mills spin tirelessly, reducing particle sizes to less than 100 microns. This grinding process releases the cocoa butter within the nibs, turning the dry nibs into a fluid, rich mass. At this stage, the chocolate liquor is either stored or immediately processed depending on the specific recipe being produced. For Hershey's signature milk chocolate, chocolate liquor alone is not enough. It must be blended with several other ingredients: sugar, milk, and cocoa butter, among others. Hershey's famously uses fresh condensed milk rather than powdered milk, a technique that imparts its distinctive flavor. Tankers bring in condensed milk that has already been pasteurized and quality tested for microbial safety. The milk is combined with sugar in large stainless steel kettles and cooked to form what is known as a milk crumb, a dry, sweet, caramelized powder that becomes the base for Hershey's milk chocolate. The milk crumb, chocolate liquor, and additional cocoa butter are blended together in massive mixers that resemble horizontal cement mixers but are built for food-grade standards. In these tumbling vessels, the blend of ingredients becomes a coarse chocolate dough. This dough is then fed through refining rollers, 5 or 6 massive polished steel rollers stacked horizontally. As the dough passes through each successive roller gap, it is compressed and sheared finer and finer, reducing the sugar and cocoa particles to just the right microscopic size to ensure a smooth texture. At this point, the chocolate still lacks the silky consistency and full flavor that people expect. That's where one of the most crucial steps in chocolate making enters: conching. Hershey's uses giant conching machines, massive, heavy-duty mixers with granite rollers that agitate, aerate, and warm the chocolate dough for hours. Traditional conching could take up to 72 hours, but with modern methods and specialized Hershey's technology, the time has been optimized without sacrificing quality. During conching, volatile acids and bitter flavors evaporate away, while cocoa and milk flavors mellow and deepen. At the same time, the continuous mixing further reduces any remaining coarse particles and disperses the cocoa butter thoroughly throughout the mass. Temperature control during conching is critical. The chocolate must stay within an exact range, typically between 130 to 180 degrees Fahrenheit, depending on the desired flavor development. Ventilation hoods draw off unwanted volatiles, and sensors embedded throughout the conches constantly report data back to automated control systems, adjusting speed and temperature as needed. Following conching, the chocolate moves into the tempering phase. Tempering is an art and science all its own. Chocolate is carefully cooled and reheated through specific temperature curves to create stable cocoa butter crystals. This gives finished chocolate its snap, gloss, and resistant to melting at room temperature. Hershey's uses continuous tempering machines which can process thousands of pounds per hour. These machines use a series of heated and cooled zones to guide the chocolate through its crystal formation journey with pinpoint accuracy. Improper tempering would result in chocolate that's dull, crumbly, or prone to blooming, a white discoloration, so this step must be executed flawlessly. Once tempered, the liquid chocolate is transported through heated pipes to the molding stations. There, automated depositors squirt precise amounts of chocolate into endless arrays of molds, some shaped for classic Hershey's bars, others for miniature versions or seasonal specialties. The molds vibrate rapidly on oscillating tables to eliminate any air bubbles and ensure an even surface. The molds then enter a long cooling tunnel, a carefully calibrated environment where the chocolate solidifies slowly and evenly. Inside the tunnel, the temperature drops gradually from around 70 degrees Fahrenheit to about 50 degrees, preventing thermal shock and ensuring that the chocolate sets with a fine, smooth crystal structure. After cooling, the solid chocolate is demolded. High-speed mechanical arms flip and flex the molds, gently releasing the perfectly formed bars onto conveyor belts. At this stage, visual inspection systems equipped with high-speed cameras and AI check every piece for uniformity, detecting even minor surface defects or molding errors. Imperfect chocolates are removed from the line for recycling back into the production process. The next step is packaging. For Hershey's bars, the chocolate rides conveyors into flow wrapping machines. Each bar is enveloped in a tight sleeve of foil and then an outer branded paper wrapper. Modern flow wrappers work at astonishing speeds, often wrapping hundreds of bars per minute with perfect precision. The wrapped bars are coded with expiration dates, batch numbers, and tracking information to ensure full traceability from production through to sale. Once wrapped, the bars are collated into cartons or retail trays by robotic packers, which arrange them neatly in boxes that are then sealed, labeled, and stacked onto pallets. Before shipment, a random sample from every production batch undergoes additional quality assurance tests, including break tests, melt tests, taste panels, and microbial analysis. Only after passing all these checks are the pallets released for distribution. The finished Hershey's milk chocolate bars then enter the logistics phase, moving through regional distribution centers that coordinate delivery to supermarkets, convenience stores, cinemas, and countless other retailers around the world. Throughout the distribution chain, temperature control remains critical. Warehouses and trucks are climate controlled to prevent the bars from experiencing temperature swings that could cause chocolate bloom or textural changes. Throughout the entire factory process, Hershey's leverages advanced automation, continuous monitoring, and decades of chocolate-making expertise to ensure that every bar tastes as iconic and consistent as the last. The level of control is extraordinary. Chocolate viscosity, particle size distribution, moisture levels, and flavor profiles are measured and adjusted in real time using sophisticated inline sensors and laboratory tests. In recent years, Hershey's has also invested heavily in sustainability, working directly with cocoa farmers through its Cocoa for Good program to promote ethical sourcing, better farming practices, and environmental stewardship. This commitment ensures not just the continued availability of high-quality cacao, but also a better future for the communities that produce it. The journey of a Kit Kat begins with two major components: the chocolate coating and the crisp wafer core. Both are manufactured separately and in parallel streams before being married together into the unmistakable Kit Kat form. Each ingredient, each layer, and each step is engineered with astonishing precision to create the perfect snap, crunch, and creamy finish that Kit Kat is famous for. The process starts with the preparation of the chocolate. Kit Kat's signature coating is slightly different from pure chocolate. It is technically a compound chocolate, specially formulated to to give a smooth melt and quick setting, properties ideal for enrobing wafers. At factories like Nestlé's York facility in the UK or similar plants worldwide, bulk cocoa liquor, cocoa butter, sugar, and milk solids are combined. The cocoa beans that form the basis of the liquor are sourced from sustainable suppliers, cleaned, roasted, and ground into fine paste months before production even begins. To prepare the chocolate coating, the cocoa liquor is blended with sugar and powdered milk in enormous stainless steel mixers. This mixture is then refined through a series of precision-calibrated rollers, reducing the particle size to around 20 microns, finer than the human tongue can detect. The refining phase is essential to create the smooth mouthfeel Kit Kat lovers expect. Following refinement, the chocolate mass moves into conching machines, where it is slowly mixed, aerated, and heated. This removes any bitter flavors and unwanted acidity, while promoting the development of a creamy, caramel-like flavor that defines Kit Kat's chocolate. Temperature control during conching is rigorously maintained at around 135 to 180 degrees Fahrenheit, depending on the recipe. Once the chocolate reaches the right flavor and viscosity, it is moved into tempering units, where it's carefully cooled and reheated to produce stable cocoa butter crystals. Proper tempering ensures that the finished chocolate will have a shiny appearance, a satisfying snap, and resistance to blooming. Meanwhile, in another section of the factory, the production of the wafer sheets is underway. Wafer batter, made from a simple mixture of wheat flour, sugar, vegetable oil, leavening agents, and water, is mixed in giant, computer-controlled vats. The batter is pumped through piping systems directly to high-speed wafer baking ovens, each stretching tens of meters in length. These wafer ovens consist of two continuously moving steel belts that sandwich the batter and pass through a baking tunnel. As the belts travel, radiant heat, conduction, and convection work together to bake the batter into ultra-thin, crisp wafer sheets. Each sheet emerges from the oven perfectly cooked, around 2 to 3 millimeters thick, with a delicate, light texture and a uniform golden brown color. After baking, the wafer sheets are rapidly cooled using forced chilled air to prevent moisture absorption. They are stacked and transported via conveyor belts to the cream spreading stations. Here, a thin layer of specially formulated filling, a mixture typically based on ground wafer crumbs, vegetable fats, sugar, and milk solids, is evenly spread across the wafers. The filling not only enhances the flavor, but also acts as a structural adhesive, bonding the multiple wafer layers together. Usually, 3 or 4 wafer sheets are stacked, with cream filling between each layer. These multi-layered blocks are then pressed under controlled pressure to ensure perfect bonding without cracking or crushing the delicate wafers. After resting for stabilization, the wafer blocks are transferred to high-speed cutting machines. The cutting process is a masterpiece of mechanical precision. Using laser guides and ultrasonic blades, the blocks are sliced first longitudinally, then crosswise into the familiar slim Kit Kat finger dimensions. Every cut must be perfect. Any deformation could later disrupt the enrobing process or spoil the iconic snap experience. Once cut, the wafer fingers are ready for enrobing. Conveyors carry them through a chocolate waterfall inside the enrobing machines. A curtain of tempered Kit Kat chocolate cascades over the wafers, completely coating them on all sides. Excess chocolate is blown off the bottom with controlled air jets, creating the thin chocolate layer underneath that gives Kit Kat its balanced chocolate to wafer ratio. Directly after enrobing, the fingers pass through a vibrating section of the conveyor to settle the chocolate coating and eliminate air bubbles. They then enter a series of cooling tunnels where cold, dry air, typically kept between 40 and 50 degrees Fahrenheit, slowly solidifies the chocolate coating without causing condensation, which would ruin the texture. At this point, the individual fingers are grouped together. Kit Kat is traditionally made with 4 fingers to a bar, although mini versions, single fingers, and chunkier variants are also produced. Robotic arms align and group the fingers with exact spacing between them before feeding them into wrapping machines. Kit Kat's iconic red and white wrapper is a masterpiece of branding and practical design. Wrapping is done using ultra-fast flow wrappers that synchronize perfectly with the grouping conveyors. Each set of fingers is enveloped in foil or a plastic laminate film, which protects against moisture and oxygen while maintaining the crunch of the wafer and the smoothness of the chocolate. The wrapping machines heat seal the edges at high speed, and rollers gently press and fold the sealed packs for that crisp, tight package finish Kit Kat is known for. As the wrapped bars move down the line, high-speed scanners and cameras inspect each package for correct seal integrity, label placement, and print clarity. Imperfections are detected in milliseconds, and defective packs are automatically ejected into collection bins for recycling. Once the Kit Kats are individually wrapped, the next stage is boxing and palletizing. Robotic case packers arrange the wrapped bars into boxes or display cartons, which are then sealed with automatic tapers and labeled with tracking information. Each box is carefully weighed and scanned to ensure it matches target specifications before being stacked onto pallets by robotic arms or palletizing machines. Throughout the entire production process, rigorous quality control is applied at every major step. Samples of chocolate, wafer batter, finished wafers, and completed bars are pooled at regular intervals for lab analysis. These tests include moisture content checks, microbiological safety testing, taste panels, and break strength tests to ensure the classic crisp break of a Kit Kat remains perfect batch after batch. In addition to inline testing, larger batch samples are subjected to accelerated aging studies to simulate how the product will perform over its shelf life. Sensory evaluation booths, staffed by trained taste testers, ensure that every batch maintains the exact flavor, aroma, texture, and mouthfeel that consumers expect. Once the Kit Kats are boxed and palletized, they are shipped out from climate-controlled distribution centers. Transport conditions are carefully managed to prevent temperature fluctuations that could cause chocolate bloom or wafer softening. Many shipments are refrigerated during summer months or in hotter climates to guarantee the product arrives in prime condition. Kit Kat's industrial production is a brilliant choreography of automation, sensory science, and quality management. Despite the high level of automation, human oversight remains crucial. Line operators monitor critical control points, adjust machine settings, respond to alarms, and carry out maintenance to keep the lines running smoothly, often 24 hours a day, 7 days a week. Recent advancements have further refined the process. State-of-the-art production lines now incorporate AI-driven predictive maintenance, allowing engineers to anticipate mechanical failures before they happen. Machine learning algorithms also optimize ingredient mixing, cooking times, and cooling profiles, subtly adjusting for real-time variables like humidity, ingredient lot variation, or slight temperature shifts in the facility. Kit Kat's commitment to sustainability is woven into production as well. Modern factories are equipped with energy recovery systems that reuse heat from the ovens and chillers. Water used in cooling and cleaning processes is recycled wherever possible. Additionally, Kit Kat's cocoa is 100% sourced through programs like Rainforest Alliance certified farms, ensuring ethical and environmentally responsible cocoa farming practices. Each Kit Kat bar that makes it into a consumer's hands is the end product of thousands of micro decisions and perfectly tuned processes: baking, layering, cutting, coating, cooling, wrapping, all executed with a level of precision that would make a Swiss watchmaker proud. The crisp snap of the break, the lightness of the wafer, the creamy melt of the chocolate, every detail is the result of decades of research, refinement, and relentless pursuit of chocolate and wafer perfection. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components, a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts equipped with vision systems scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every almond joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for almond joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the tenth of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from coconut grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. Hershey's chocolate bars begin their journey long before they ever reach a factory. It all starts with the cocoa bean, the essential ingredient that gives chocolate its signature taste. Cocoa trees grow in the tropical regions of West Africa, South America, and Southeast Asia, where warm temperatures and high humidity create the perfect environment for cacao cultivation. Farmers carefully harvest ripe cocoa pods, slicing them open to extract the cocoa beans nestled inside. These beans are then piled into large heaps or wooden boxes, where they undergo fermentation, a crucial process that develops the deep, complex chocolate flavors. Over several days, the beans are stirred occasionally, allowing natural yeast and bacteria to work their magic. The result is a transformation from bitter, raw cocoa to something much closer to the chocolate taste that will eventually be refined and perfected in Hershey's factories. Once fermentation is complete, the cocoa beans are spread out under the sun to dry. Farmers rake them periodically to ensure even drying, preventing mold growth and preserving the beans' quality. This drying process can take up to a week, depending on weather conditions. When fully dried, the beans are packed into burlap sacks and shipped across the world to Hershey's chocolate production facilities. The journey from farm to factory is carefully monitored, as the quality of the beans at this stage will significantly influence the final product's taste and texture. Upon arrival at the Hershey factory, the cocoa beans go through a strict quality control process. They are first inspected for size, color, and overall condition. Any beans that do not meet the company's rigorous standards are removed from the batch. Next, the beans are thoroughly cleaned to remove any dust, dirt, or foreign matter that may have accumulated during transport. High-powered air jets and mechanical sifters separate unwanted debris, ensuring that only pure cocoa beans proceed to the next stage. Once cleaned, the cocoa beans move into the roasting phase. Roasting is one of the most important steps in chocolate production, as it intensifies the flavor and brings out the rich, aromatic notes associated with Hershey's signature taste. The beans are poured into large rotating drum roasters, where they are exposed to controlled heat for a specific duration. The precise temperature and roasting time are carefully calibrated based on the desired flavor profile. As the beans roast, their moisture content decreases, and chemical changes occur within the beans, developing the characteristic chocolatey taste. The air inside the roasters is constantly circulated to ensure even roasting, and sensors monitor the temperature to maintain consistency. Once the beans have been roasted to perfection, they are transferred to the winnowing machines. Here, the beans are cracked open, breaking them into smaller fragments called nibs. The outer shells, which are no longer needed, are blown away using air currents, leaving only the rich, flavorful cocoa nibs behind. These nibs contain the essence of chocolate, and they will soon be transformed into a smooth, creamy liquid that serves as the foundation for Hershey's chocolate bars. Meanwhile, another critical ingredient in Hershey's chocolate is being prepared: milk. One of the distinguishing features of Hershey's chocolate is its unique milk treatment process, which contributes to its recognizable flavor. Fresh milk is sourced from dairy farms located near the Hershey factory to ensure freshness. Upon arrival, the milk undergoes pasteurization, a heating process that eliminates harmful bacteria while preserving its nutritional qualities. The milk is then condensed and mixed with sugar, creating a rich, sweetened milk base that will later be combined with the cocoa ingredients. As the cocoa nibs continue their transformation, they are sent to grinding machines, where they are crushed into a thick, liquid paste known as chocolate liquor. Despite the name, chocolate liquor contains no alcohol. It is simply the finely ground form of cocoa solids suspended in cocoa butter. The grinding process generates heat, which helps break down the cocoa particles even further, creating a smooth consistency. The quality of this chocolate liquor is crucial, as it will determine the texture and taste of the final chocolate product. Once the chocolate liquor is ready, it is blended with the sweetened condensed milk mixture, along with additional cocoa butter and sugar. These ingredients come together in large industrial mixers, where they are thoroughly blended to create a uniform chocolate mixture. The goal at this stage is to ensure even distribution of flavors, so the chocolate undergoes multiple rounds of mixing and refining. The refining process is carried out using heavy steel rollers, which reduce the particle size of the chocolate to an ultra-fine consistency. This step is essential for achieving the smooth texture that Hershey's chocolate bars are known for. After refining, the chocolate mixture moves into the conching phase, a process named after the shell-like shape of the original conching machines. Conching involves continuously churning and aerating the chocolate for several hours, helping to develop a silky texture and deepening the flavor. The friction generated by the conching machines warms the chocolate slightly, allowing undesirable acidity and bitterness to dissipate while enhancing the overall creaminess. Hershey's carefully controls the conching process to achieve a balance of flavors that has remained consistent for over a century. Once conching is complete, the chocolate is not yet ready to be molded into bars. It must first undergo tempering. Tempering is a delicate process that involves heating and cooling the chocolate in a precise manner to stabilize the cocoa butter crystals. If chocolate is not properly tempered, it can develop a dull appearance, a grainy texture, or white streaks known as bloom. To prevent this, Hershey's employs advanced tempering machines that carefully regulate the temperature changes, ensuring that the chocolate maintains a glossy finish and a firm, satisfying snap when broken. With the chocolate now perfectly tempered, it is ready to be molded into the iconic Hershey's chocolate bar shape. Liquid chocolate flows into custom-designed molds that feature the signature rectangular segments, each embossed with the Hershey's logo. These molds travel along a conveyor belt through a cooling tunnel, where the chocolate gradually solidifies. The cooling process is precisely controlled to ensure even crystallization, which contributes to the final bar's smooth texture and structure. Once the chocolate has fully set, the bars are carefully removed from the molds and inspected for any imperfections. While the chocolate bars are being formed, the packaging materials are also being prepared. Hershey's chocolate bars are wrapped in a combination of foil and paper, a packaging style that has remained largely unchanged for decades. The foil wrapping helps protect the chocolate from moisture and light, preserving its freshness and preventing it from developing off flavors. The outer paper wrapper, printed with the familiar Hershey's branding, serves as both an aesthetic and informational component, providing details about the product while reinforcing the brand's legacy. As the tempered chocolate flows through the production line, it is maintained at an exact temperature to prevent premature setting. Hershey's factories employ state-of-the-art computerized systems that regulate every aspect of the chocolate's movement, ensuring that the liquid chocolate maintains the ideal viscosity. If the chocolate is too thick, it may not fill the molds evenly. If it is too thin, it may not develop the proper texture once solidified. To maintain this delicate balance, specialized flow control pumps continuously circulate the chocolate through insulated pipes that keep it warm and fluid until the exact moment it is deposited into the molds. The molds themselves are engineered with extreme precision to create the uniform shape and smooth surface that Hershey's chocolate bars are known for. Each mold is made from food-grade polycarbonate material, designed to withstand repeated use while maintaining an ultra-smooth interior that ensures the chocolate releases cleanly once set. These molds travel along a high-speed conveyor belt system, positioned beneath nozzles that dispense the precise amount of liquid chocolate needed to form each bar. Advanced sensors monitor the filling process, making real-time adjustments to ensure that every mold receives an identical amount of chocolate. Once the molds are filled, the next critical step in the process is vibration. The conveyor belt moves the freshly filled molds to a specialized vibrating platform, which gently shakes them at a controlled frequency. This step serves two important purposes. First, it helps remove any trapped air bubbles that could create holes or uneven textures in the final product. Second, it ensures that the chocolate settles evenly within the mold, creating a smooth and uniform appearance. Even the slightest inconsistency in this stage could lead to defects in the bars, so Hershey's quality control team continuously monitors the process to maintain consistency. After vibration, the molds enter a cooling tunnel, a long temperature-controlled chamber that gradually reduces the chocolate's temperature to encourage proper crystallization. This step is crucial for achieving the perfect texture and preventing unwanted fat bloom, which can occur when cocoa butter crystallizes improperly, resulting in a white, powdery appearance on the surface of the chocolate. The cooling tunnel is divided into multiple temperature zones, allowing the chocolate to solidify gradually rather than cooling too quickly, which could cause structural weaknesses or affect the snap of the final bar. As the chocolate sets, it undergoes another round of automated inspection to detect any irregularities. High-resolution cameras and laser scanners analyze each mold, checking for inconsistencies in shape, texture, or surface quality. Any bars that do not meet Hershey's exacting standards are rejected and sent back for remelting, ensuring that no chocolate goes to waste. Once the bars pass inspection, they are gently removed from the molds using an automated demolding system. A combination of slight flexing and compressed air helps separate the bars from the molds without damaging their delicate structure. Now that the chocolate bars have taken their final shape, they must be prepared for packaging. Hershey's packaging process is one of the most sophisticated in the confectionery industry, designed to ensure that each bar remains fresh and protected from environmental factors such as moisture, temperature fluctuations, and physical damage. The first step in packaging involves a high-speed wrapping machine that envelopes each bar in a layer of aluminum foil. This foil serves as a crucial barrier against light and oxygen, both of which can negatively impact the flavor and quality of the chocolate over time. Once the bars are wrapped in foil, they move to the next stage, where the outer paper wrapper is applied. Hershey's iconic packaging, with its bold brown and white branding, is instantly recognizable and has remained largely unchanged for decades. The wrapping machine applies a thin bead of adhesive to secure the paper wrapper in place, ensuring that it remains tightly sealed around the foil-covered chocolate bar. Automated sensors check each wrapped bar for proper alignment, rejecting any that do not meet the strict packaging criteria. With individual bars now fully wrapped, the next step is bundling them into larger packs. Depending on the intended retail format, Hershey's chocolate bars may be packaged as single units, multi-packs, or larger bulk boxes for wholesale distribution. Robotic arms carefully arrange the wrapped bars into predetermined configurations, stacking them into cardboard trays or shrink-wrapped bundles. For multi-packs, additional layers of protective film are applied to keep the bars securely together, preventing shifting during transportation. As the packaged chocolate bars move down the production line, they are assigned a unique batch code and expiration date, which are printed onto each wrapper using high-speed inkjet printers. This information is essential for inventory tracking, ensuring that products are rotated properly in warehouses and retail stores. It also allows Hershey's quality control team to trace any potential issues back to a specific production batch if necessary. Once all packaging steps are complete, the finished Hershey's chocolate bars are sent through final inspection before being prepared for shipment. Automated weight sensors check each package to ensure that no product is missing or underweight. Any deviations from the standard weight result in the package being removed from the line for manual inspection. After passing this final quality check, the bars are packed into large shipping cartons, which are sealed and labeled for distribution. The shipping process is a carefully orchestrated operation designed to maintain the integrity of the chocolate during transit. Hershey's distribution centers are equipped with climate-controlled storage areas, ensuring that chocolate is kept at an optimal temperature before being shipped to retailers worldwide. The pallets of chocolate bars are loaded onto refrigerated trucks, which maintain a consistent temperature to prevent melting or fat bloom. During summer months or in regions with particularly hot climates, additional measures are taken, such as using insulated packaging to further protect the chocolate from heat exposure. From the distribution centers, Hershey's chocolate bars are shipped to grocery stores, convenience stores, vending machines, and online retailers. The entire process, from sourcing cocoa beans to the moment a consumer unwraps a bar, is the result of years of expertise, precise engineering, and a deep commitment to quality. Hershey's has spent over a century refining its production methods, leveraging cutting-edge technology while preserving the craftsmanship that has made its chocolate a household favorite. Even after reaching store shelves, Hershey's continues to monitor product freshness through a network of distributors and retail partners. Inventory rotation practices ensure that consumers always receive the freshest possible product, with older stock being sold before newer shipments are placed on shelves. The brand's commitment to quality extends beyond just manufacturing. It includes every aspect of the supply chain, from sourcing raw ingredients to delivering the final product into the hands of consumers. As the packaged chocolate bars leave the production line, they move through an automated sorting system that directs them to the correct pallets for shipment. Robotic arms, programmed with artificial intelligence and real-time scanning capabilities, ensure that each batch is assigned to the right destination. Whether the chocolate bars are heading to domestic supermarkets, international retailers, or specialized distributors, each shipment is meticulously tracked using barcode scanning and digital inventory management systems. Hershey's has invested heavily in supply chain optimization, integrating real-time data analytics to monitor product flow, track expiration dates, and prevent overstocking or shortages. The process of transporting chocolate requires specific environmental controls. Hershey's distribution centers are equipped with temperature-controlled storage facilities to prevent the chocolate from being exposed to excessive heat or humidity. If chocolate bars are stored in less than ideal conditions, the risk of bloom increases. Fat bloom, the most common issue, occurs when the cocoa butter in the chocolate migrates to the surface, creating a dull, whitish coating. Sugar bloom, on the other hand, happens when moisture causes sugar crystals to form on the surface of the chocolate, resulting in a rough texture. While neither of these phenomena makes the chocolate unsafe to eat, they can negatively impact consumer perception and overall product quality. To prevent these issues, Hershey's carefully maintained storage temperatures between 65 degrees Fahrenheit and 70 degrees Fahrenheit, ensuring that the chocolate remains in optimal condition before it reaches retailers. Once the chocolate bars are loaded onto trucks, their journey continues. Hershey's logistics team coordinates shipments using a combination of ground transportation, air freight, and sea freight, depending on the destination. Domestic shipments typically travel via temperature-controlled trucks, while international shipments require specialized shipping containers equipped with insulation and climate control technology. Each step of transportation is monitored to ensure that the chocolate remains in a stable environment, preventing any degradation in quality. At retail distribution centers, Hershey's chocolate bars are unloaded and sorted based on regional demand. Large grocery chains and supermarkets often have automated warehouse systems that use conveyor belts and robotic picking technology to distribute inventory efficiently. Hershey's works closely with retailers to ensure that the product is stocked properly, preventing situations where chocolate sits in storage too long before being placed on shelves. This level of coordination ensures that customers receive the freshest possible product. Inside stores, Hershey's chocolate bars are positioned strategically to maximize sales. The company's marketing and sales teams work with retailers to determine optimal placement, typically near checkout aisles, in candy sections, and in promotional display stands designed to attract impulse buyers. Hershey's has spent years researching consumer behavior, using data-driven insights to refine its approach to in-store merchandising. Seasonal variations such as Halloween, Christmas, and Valentine's Day bring about limited edition packaging and themed chocolate products that are prominently displayed to boost sales during peak shopping periods. While the chocolate bars are now readily available for purchase, Hershey's commitment to quality control does not stop at the point of sale. The company maintains a rigorous consumer feedback system, allowing customers to report any quality concerns or irregularities. If a batch of chocolate bars is found to have any defects, Hershey's can trace the issue back to a specific production lot using the batch codes printed on each wrapper. This traceability ensures that any necessary corrective actions, such as recalls or reformulation, can be implemented quickly and efficiently. Hershey's also invests heavily in food safety measures, adhering to strict regulatory standards set by organizations such as the US Food and Drug Administration, FDA, the Food Safety Modernization Act, FSMA, and global food safety initiatives. In addition to routine quality checks throughout production, the company conducts random sampling of finished chocolate bars to test for microbial contamination, ingredient consistency, and adherence to allergen labeling guidelines. Every aspect of production, from ingredient sourcing to final packaging, is governed by good manufacturing practices, GMP, to ensure consumer safety. Beyond the standard Hershey's milk chocolate bar, the company's factories are also responsible for producing a variety of chocolate products that follow similar manufacturing principles, but may involve additional steps. For example, Hershey's with almonds requires an extra stage where roasted almonds are added to the chocolate mixture before molding. Similarly, cookies and cream variations include white chocolate blended with crunchy cocoa cookie pieces, requiring specialized mixing equipment to distribute the inclusions evenly throughout the bar. These variations highlight the flexibility of Hershey's production facilities, which are designed to accommodate multiple product lines while maintaining consistent quality. Sustainability has become an increasing focus for Hershey's in recent years. The company has taken significant steps toward reducing its environmental impact, particularly in cocoa sourcing and packaging waste reduction. Through its Cocoa for Good initiative, Hershey's invests in sustainable cocoa farming practices, providing training and financial support to farmers in West Africa and Latin America. These efforts not only help improve cocoa yields, but also ensure ethical labor practices and environmental conservation. Additionally, Hershey's has committed to using more recyclable packaging materials, reducing plastic waste in its supply chain, and lowering its carbon footprint through energy-efficient manufacturing practices. Innovation continues to drive the future of Hershey's chocolate bars. The company's research and development teams are constantly exploring new formulations, textures, and flavors to keep up with changing consumer preferences. Whether it's introducing sugar-free or plant-based chocolate alternatives, experimenting with new ingredients, or enhancing the nutritional profile of its products, Hershey's remains at the forefront of confectionery innovation. The brand has also embraced digital marketing and e-commerce, expanding its presence in online grocery platforms, direct-to-consumer sales, and subscription-based chocolate delivery services. Despite all the advancements in production technology and distribution, the core experience of enjoying a Hershey's chocolate bar remains unchanged. The familiar taste, creamy texture, and satisfying snap of the chocolate have made it a beloved treat for generations. Each bar carries with it the legacy of Milton Hershey's original vision, a high-quality chocolate product that is both accessible and affordable to consumers around the world. Looking ahead, Hershey's will continue to evolve, adapting to new market demands while staying true to the craftsmanship and quality that have defined the brand for over a century. As technology progresses, automation and artificial intelligence will play an even greater role in optimizing production efficiency, ensuring that every Hershey's chocolate bar maintains the same level of consistency and excellence. The commitment to quality, sustainability, and innovation will continue to shape the future of Hershey's chocolate, ensuring that it remains a staple in households for generations to come. The Hershey's chocolate bar, a product that has been enjoyed for over a century, is the result of a complex and highly controlled manufacturing process that blends tradition with cutting-edge technology. While the chocolate has already gone through its journey from raw cocoa beans to finished bars, wrapped and ready for sale, the process does not end there. The company continues to ensure product integrity even after distribution, keeping an eye on market trends, customer satisfaction, and ongoing improvements in production methods. Once the chocolate bars reach stores, Hershey's relies on a vast retail network to keep the product readily available for consumers. Supermarkets, convenience stores, vending machines, and online retailers all play a role in ensuring that Hershey's chocolate bars are accessible in virtually every corner of the market. In addition to traditional sales channels, Hershey's has expanded into direct-to-consumer models, offering limited edition flavors and exclusive packaging through its website and specialty stores. This move allows consumers to order their favorite Hershey's products from the comfort of their homes, ensuring freshness and convenience. Marketing plays a crucial role in maintaining Hershey's dominance in the chocolate industry. The brand has built an emotional connection with consumers, often associating its chocolate bars with childhood nostalgia, holidays, and shared moments. Advertising campaigns, social media promotions, and in-store displays reinforce the brand's image, keeping it relevant across generations. Hershey's also engages in sponsorships and collaborations, partnering with other food companies to create innovative products such as Hershey's infused baked goods, cereals, and ice cream flavors. Quality control remains a top priority even after the bars leave the factory. Hershey's has consumer feedback channels where customers can report any issues such as damaged packaging or quality inconsistencies. The company takes such feedback seriously, using it to refine manufacturing processes and enhance overall product quality. If a defect is traced back to a specific batch, Hershey's can quickly analyze production data to determine the cause and prevent future occurrences. This level of traceability is made possible by sophisticated tracking systems that log every step of the manufacturing and distribution process. Sustainability continues to be an integral part of Hershey's long-term vision. The company is committed to ethical cocoa sourcing, reducing carbon emissions, and minimizing waste in its production facilities. Efforts include switching to more eco-friendly packaging materials, optimizing energy use in factories, and investing in cocoa farming communities to improve agricultural sustainability. By implementing these initiatives, Hershey's aims to balance business growth with environmental responsibility, ensuring that future generations can continue to enjoy its chocolate without negatively impacting the planet. Innovation is also a driving force behind Hershey's success. The company constantly experiments with new flavors, textures, and formulations, responding to emerging consumer trends such as sugar-free, high-protein, and plant-based alternatives. Research and development teams work on improving not only the taste, but also the nutritional profile of chocolate, making it more appealing to health-conscious consumers. Additionally, Hershey's has explored advancements in manufacturing efficiency, incorporating AI-driven quality checks, automation in packaging, and precision temperature control systems to maintain the highest standards in chocolate production. Despite all these advancements, the core experience of enjoying a Hershey's chocolate bar remains timeless. The simple act of unwrapping a bar, breaking off a square, and savoring the smooth, creamy texture is a universal pleasure that spans generations. Hershey's success lies in its ability to evolve while staying true to its heritage, ensuring that the chocolate remains as beloved today as it was when Milton Hershey first introduced it. Looking forward, Hershey's will continue to adapt to changing market dynamics while upholding the traditions that have defined its chocolate for over a century. Whether through expanding into new markets, refining sustainability practices, or leveraging technological innovations, the brand remains committed to delivering the same high-quality chocolate experience that consumers know and love. From the cocoa farms where it all begins to the final moment when a Hershey's chocolate bar is enjoyed, every step in the process is a testament to dedication, precision, and the enduring appeal of one of the world's most iconic chocolate brands. Producing the world's most beloved chocolate bars isn't just about great ingredients, it's a precision-driven process on an unbelievable scale. Every day, millions of Cadbury Dairy Milk bars are crafted inside state-of-the-art factories, where advanced machinery and carefully refined techniques transform raw cocoa into the smooth, creamy chocolate people love. The creation of a Cadbury Dairy Milk bar begins long before the chocolate reaches the factory. It starts on cacao farms located in tropical regions near the equator, where the conditions are ideal for growing cacao trees. The trees require warm temperatures, high humidity, and consistent rainfall to produce the cacao pods that contain the beans essential for making chocolate. These pods grow directly from the branches and trunk of the tree, taking around 6 months to mature. Farmers carefully monitor the pods, waiting until they turn from green to yellow, orange, or deep red, indicating ripeness. Harvesting is a meticulous process, as improper handling can damage the delicate cacao tree. Skilled workers use sharp machetes to cut the ripe pods from the tree, ensuring that the branch is left intact so that future pods can develop. Once harvested, the cacao pods must be processed immediately to prevent spoilage. The first step involves cracking open the thick, leathery shells to reveal the beans inside, which are surrounded by a sweet, sticky pulp. Farmers often use wooden clubs or knives to split the pods, being careful not to damage the beans within. Each pod contains around 30 to 50 beans, and thousands of these are needed to produce a single chocolate bar. The extracted beans and pulp are then placed into large wooden fermentation boxes, which are arranged in stacks to allow for air circulation. Fermentation is a crucial step in the chocolate making process, as it develops the complex flavors that will later be enhanced during roasting. The beans are left to ferment for 5 to 8 days, during which time they undergo chemical changes that transform their taste. The natural yeasts in the pulp break down the sugars, generating heat and causing the temperature inside the fermentation boxes to rise. This heat triggers biochemical reactions within the beans, breaking down their natural bitterness and releasing the precursor compounds that will later give chocolate its distinctive aroma and flavor. To ensure even fermentation, workers turn the beans periodically, usually once a day. This helps to distribute heat and oxygen throughout the pile while allowing excess moisture to evaporate. During this time, the beans gradually darken in color and develop a rich, earthy aroma. Without proper fermentation, the beans would retain a raw, astringent taste, resulting in low-quality chocolate. After fermentation is complete, the beans must be dried to reduce their moisture content and prepare them for transport. Traditionally, drying is done by spreading the beans out on large wooden trays or concrete surfaces under the sun. The drying process can take anywhere from 5 to 7 days, depending on the weather conditions. Workers frequently rake the beans to ensure they dry evenly and prevent mold growth. If the climate is too humid or rainy, mechanical dryers may be used to speed up the process and maintain quality standards. Once fully dried, the cacao beans are carefully sorted to remove any defective or damaged ones before being packed into jute sacks for shipment. These sacks are transported from cacao-producing countries to chocolate manufacturing facilities worldwide, including those used by Cadbury. Upon arrival at the factory, the first step in the production process is cleaning. The beans are loaded onto conveyor belts and passed through a series of cleaning machines that remove dirt, dust, and any remaining plant material. This ensures that only the highest quality beans proceed to the next stage. After cleaning, the beans are roasted to further develop their flavor. The roasting process is highly controlled, with temperatures and durations carefully calibrated to achieve the desired taste profile. The exact roasting conditions vary depending on the type of chocolate being produced, but for Cadbury Dairy Milk, the beans are typically roasted at temperatures between 120 to 150 degrees Celsius for about 30 to 45 minutes. During roasting, the beans undergo the Maillard reaction, a chemical process that enhances their flavor and aroma by breaking down proteins and sugars. The heat also causes the thin outer shells of the beans to become brittle, making them easier to remove in the next step. Once roasting is complete, the beans are cooled and sent through a machine called a winnower. This machine cracks the beans open, separating the outer shells from the inner nibs. The shells are removed using powerful air jets, leaving behind the pure cacao nibs, which contain the essential cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, liquid paste known as cocoa mass or cocoa liquor. This process is done using industrial grinding machines that apply high pressure to break down the nibs into tiny particles. The resulting cocoa mass has a rich, intense chocolate flavor, but is still quite coarse in texture. At this stage, the cocoa mass can be further processed to extract cocoa butter, a key ingredient in chocolate making. The mass is placed into hydraulic presses, which apply immense pressure to separate the fat, cocoa butter, from the solid components, cocoa solids. The extracted cocoa butter is a pale yellow, creamy substance that gives chocolate its smooth and creamy mouthfeel. Meanwhile, the remaining cocoa solids are ground into a fine powder, which can be used for making cocoa powder or reintroduced into the chocolate mixture for added richness. For Cadbury Dairy Milk, the next crucial step is blending the cocoa mass with other key ingredients, sugar and milk powder. Unlike dark chocolate, which relies on cocoa solids as the primary component, dairy milk chocolate has a significant proportion of milk, giving it a distinctively creamy texture and flavor. Cadbury uses fresh milk in its production process rather than relying solely on milk powder, a method that differentiates its chocolate from many other brands. The fresh milk is collected from dairy farms and transported in refrigerated tankers to the factory, where it undergoes quality control checks to ensure purity and freshness. Upon arrival, the milk is pasteurized to eliminate harmful bacteria and then concentrated to reduce its water content. This is achieved through a process called vacuum evaporation, in which the milk is heated under reduced pressure to remove excess moisture while preserving its natural flavor. The concentrated milk is then mixed with sugar to form a sweetened milk mixture, which is later blended with the cocoa mass. This unique approach, known as the crumb process, involves heating the milk and sugar together before adding them to the chocolate mixture. This technique enhances the caramelized notes of the chocolate and contributes to Cadbury's signature flavor. Once the cocoa mass, milk, and sugar are combined, the mixture undergoes refining to achieve a smooth consistency. Industrial refining machines use heavy rollers to grind the chocolate mixture, reducing the particle size to an ultra-fine level. This step is essential for creating the smooth, velvety texture that defines Cadbury Dairy Milk. If the particles are too large, the chocolate will have a grainy, rough mouthfeel, so precision in refining is crucial. The refined chocolate mixture, now resembling a dry, powdery substance, is ready for the next stage, conching. Conching is a continuous mixing and aeration process that further develops the chocolate's flavor and texture. The mixture is placed into large conching machines, where it is continuously stirred and heated for several hours. The duration of conching varies depending on the desired final texture and flavor, but for Cadbury Dairy Milk, it typically lasts between 4 to 6 hours. During this process, the chocolate's acidity and bitterness are reduced, while the smoothness and richness are enhanced. The heat and friction generated during conching also help to distribute the cocoa butter evenly, ensuring that the chocolate has a uniform texture. Once the conching process has refined the chocolate mixture into a smooth and well-developed liquid, it must undergo a crucial process known as tempering. Tempering is an essential step in chocolate production that ensures the final chocolate bars have a glossy finish, a firm structure, and the characteristic snap when broken. This process involves carefully controlling the temperature of the chocolate to stabilize the cocoa butter crystals. Cocoa butter exists in multiple crystalline forms, but only one of them, the beta crystal structure, provides the ideal texture and appearance for chocolate bars. If the chocolate is not tempered correctly, it can develop an unattractive, dull or streaky surface and a grainy texture. Tempering is achieved through a series of precise temperature adjustments. First, the liquid chocolate is gradually cooled to around 27 to 28 degrees Celsius, which encourages the formation of stable beta crystals. Then, the temperature is raised slightly to about 31 to 32 degrees Celsius for milk chocolate, melting any unwanted crystal structures while keeping the stable ones intact. This ensures that when the chocolate cools and solidifies in the molds, it will have a smooth and uniform consistency. Large-scale chocolate tempering machines, which are fully automated, are used in Cadbury's factories to maintain this process with extreme precision. These machines continuously agitate the chocolate while controlling its temperature at various stages, ensuring that the cocoa butter crystallizes correctly. Once tempering is complete, the chocolate is ready for molding. The tempered chocolate is transferred to an automated molding system where it is poured into specially designed molds that give Cadbury Dairy Milk bars their iconic shape and thickness. The molds are made of food-grade polycarbonate plastic or stainless steel and are designed to create perfectly uniform chocolate bars. The molding system ensures that each bar receives the precise amount of liquid chocolate needed for consistent weight and shape. To ensure that the chocolate fills every crevice of the mold and eliminates any trapped air bubbles, the molds pass through a vibrating station. This high-frequency vibration gently shakes the molds, allowing the liquid chocolate to settle evenly and remove any unwanted air pockets. This step is crucial in creating a uniform texture throughout the bar, as any trapped air can lead to weak spots or inconsistencies in the final product. Once the chocolate is evenly distributed in the molds, the bars must be cooled to solidify completely. The molds move along a conveyor belt into a cooling tunnel, a temperature-controlled environment that gradually reduces the temperature of the chocolate. Cooling must be done gradually to prevent the formation of sugar or fat bloom, which can create a white or grayish appearance on the surface of the chocolate. The cooling tunnels are typically set at temperatures between 5 to 10 degrees Celsius, and the bars spend around 20, 30 minutes inside, depending on their thickness and size. During this time, the chocolate transitions from a liquid state to a solid form with a firm structure and smooth texture. After cooling, the solidified chocolate bars are carefully removed from the molds using an automated demolding system. This process is designed to be gentle to prevent breakage, ensuring that each bar maintains its perfect shape. The bars are then sent along conveyor belts for the next stage, quality inspection. At this point, every chocolate bar undergoes a thorough quality control check to ensure it meets Cadbury's strict standards. High-speed cameras and laser sensors scan the chocolate bars for any imperfections, such as cracks, air bubbles, or irregular shapes. Bars that do not meet quality standards are removed from the production line and either reprocessed or discarded. Factory workers also conduct random manual inspections, checking for surface smoothness, uniform thickness, and the signature Cadbury Dairy Milk texture. Once the bars have passed the quality inspection stage, they move on to the packaging process. Packaging is an essential part of chocolate production, as it protects the chocolate from external factors such as moisture, air, and temperature changes that could affect its quality. The packaging process begins with automated machines wrapping each chocolate bar in a protective layer. Traditionally, Cadbury Dairy Milk bars were wrapped in foil with a paper sleeve. but modern packaging now consists of a specially designed plastic film that provides better sealing and protection. The packaging machines work at incredibly high speeds, wrapping hundreds of chocolate bars per minute. Each bar is precisely aligned and fed into the packaging machine, where the plastic film is cut and wrapped tightly around it. Heat sealing technology ensures that the package is securely sealed, keeping the chocolate fresh and protected from environmental factors. Once wrapped, the bars are sent through a labeling station, where product information such as batch numbers, expiration dates, and barcodes are printed onto the packaging. After labeling, the individually wrapped chocolate bars are grouped together into larger multi-packs or cartons, depending on the intended retail format. These multi-packs are then placed into shipping boxes, which are sealed and prepared for distribution. To ensure efficiency in the supply chain, Cadbury's factory uses automated robotic systems to stack the finished boxes onto pallets. These robotic arms work with incredible precision, organizing the boxes in a way that maximizes space while ensuring stability during transport. The pallets of Cadbury Dairy Milk bars are then transferred to the factory's storage and distribution center, where they are kept in temperature-controlled warehouses before being shipped to retailers worldwide. The storage conditions are carefully maintained to prevent temperature fluctuations, as chocolate is highly sensitive to heat and humidity. Ideal storage temperatures for chocolate typically range between 15 to 18 degrees Celsius to prevent melting, fat bloom, or sugar crystallization. Once ready for distribution, the chocolate bars are loaded onto refrigerated trucks and transported to supermarkets, convenience stores, and other retail outlets. Cadbury ensures that strict logistics and transportation protocols are followed to maintain the quality of the chocolate during transit. These trucks are equipped with temperature-controlled systems that prevent overheating or exposure to extreme temperatures, ensuring that the chocolate arrives in perfect condition. Upon arrival at retail locations, the chocolate bars are displayed on store shelves, ready for consumers to purchase. The iconic purple packaging and recognizable branding make Cadbury Dairy Milk one of the most easily identifiable chocolate products on the market. From the initial stages of cacao cultivation to the moment a customer unwraps a bar, every step in the production process is meticulously designed to deliver the perfect balance of smoothness, creaminess, and rich chocolate flavor that has made Cadbury Dairy Milk a favorite for generations. The next stage in the manufacturing process is focused on large-scale efficiency, ensuring that every single Cadbury Dairy Milk bar produced maintains the same level of quality, texture, and taste. Once the bars are molded, cooled, and packaged, the production line moves seamlessly into the next critical phase: quality control and inspection. While some initial checks were already performed during molding and packaging, this stage is dedicated to an in-depth analysis of every batch to guarantee consistency. Cadbury employs an extensive quality control system using a combination of automated technology and human oversight. High-speed cameras and infrared scanners are positioned along the conveyor belts to detect any visible imperfections, such as cracks, surface defects, or uneven molding. These sophisticated imaging systems compare each chocolate bar against a pre-programmed reference model, instantly flagging any inconsistencies. Defective bars are automatically removed from the production line and sent to a separate area where they may be either reprocessed or discarded depending on the severity of the defect. Beyond the physical appearance of the bars, texture and taste are also key factors that must be evaluated. Every production batch undergoes sample testing, where factory workers manually inspect a random selection of bars, breaking them to listen for the characteristic snap that signifies proper tempering. The texture is also analyzed using precision measuring instruments that evaluate the chocolate's density and uniformity. To maintain Cadbury's signature creamy mouthfeel, particle size analysis is conducted to ensure that the chocolate's refined mixture maintains a smooth consistency. If any deviations are detected, the production settings are adjusted in real time to correct potential issues before they impact the entire batch. In addition to visual and textural inspections, extensive taste testing is performed. Cadbury employs trained sensory panels, experts with highly developed palates, to sample and evaluate each batch of dairy milk chocolate. These professionals assess the chocolate for its signature balance of sweetness, creaminess, and cocoa richness. The sensory panelists follow a structured evaluation process, examining attributes such as melt rate, lingering aftertaste, and flavor complexity. To ensure objective results, the tasters follow strict guidelines, such as cleansing their palates between samples and tasting in a controlled environment, free from external odors or distractions. Once the quality control stage is successfully completed, the chocolate bars proceed to the final stage of distribution. At this point, thousands of bars are packed into cartons and prepared for shipment. The logistics of distributing Cadbury Dairy Milk bars to retailers worldwide is a highly coordinated effort. Each carton is scanned, labeled, and sorted based on its destination. Advanced inventory management systems track every unit in real time, ensuring that supply chain operations remain smooth and efficient. Temperature-controlled storage is an essential part of this process. Since chocolate is highly sensitive to temperature and humidity, Cadbury warehouses maintain precise environmental conditions. Storage temperatures are carefully kept within the optimal range of 15 to 18 degrees Celsius to prevent issues such as fat bloom, a white discoloration caused by fat migration, or sugar bloom, a grainy surface texture caused by moisture exposure. To further protect the chocolate, humidity levels in the warehouse are monitored to prevent condensation from forming inside the packaging. Once the chocolate bars are ready for transport, they are loaded onto specially designed delivery trucks equipped with temperature regulation systems. These vehicles are programmed to maintain ideal conditions throughout transit, ensuring that the chocolate does not melt or suffer quality degradation. The bars are then transported to distribution centers, where they are sorted and prepared for delivery to supermarkets, convenience stores, and online retailers. The final stage of the Cadbury Dairy Milk Bar's journey, from its creation in the factory to reaching the hands of consumers, is a combination of advanced logistics, careful storage, and precise distribution. Ensuring that millions of chocolate bars arrive in perfect condition across the globe requires an intricate supply chain,